Hello everyone, and welcome to video number 2, covering subtopic 5.5, Entropy and Spontaneity from topic 5 of energetics. In the first video, we discussed the concept of entropy. In this video, we will cover the concept of spontaneity of chemical reactions. I've started by defining what a spontaneous reaction is. A spontaneous reaction is a reaction that occurs without any outside influence. Basically, at any given temperature, if a reaction takes place spontaneously without any outside influence from us, such as heating the reaction system, then the reaction occurs spontaneously. Otherwise, if they do not react at that temperature, it doesn't mean that the reaction cannot be spontaneous ever. It means that it is not spontaneous at that particular temperature, and it can sometimes be made to be spontaneous by outside influence such as heating the reaction mixture. But a spontaneous reaction is a reaction that occurs without any outside influence at any given temperature. The spontaneity of a reaction is determined using the Gibbs free energy change of a reaction. Gibbs free energy change of a reaction, which is given the symbol delta G, standard of a reaction as stated here. Normally, in class, I would explain what Gibbs free energy is, because this is Gibbs free energy change, delta G. We have learned what entropy is and what entropy change is. We have learned what enthalpy is and what enthalpy change is. But in the IB syllabus, you are only required to learn Gibbs free energy change of reaction without actually learning what Gibbs free energy is. When we get back to school, I will cover Gibbs free energy and explain it to you. But according to the syllabus, we will only learn in this video how to calculate the Gibbs free energy change of a reaction, which will help determine the spontaneity of any chemical reaction. The Gibbs free energy change of a reaction is calculated using this equation over here. The Gibbs free energy change of a reaction is calculated by calculating the enthalpy change of a reaction, which can be calculated in 3 ways. As we learned in previous videos, we can calculate it using the enthalpy change of formation cycles, or enthalpy change of combustion cycles, or bond enthalpies. And thus, we have learned how to determine the enthalpy change of any reaction, the units of which will be in kilojoule per mole. And then, after calculating the enthalpy change of a reaction, we will subtract the product of the temperature at which the reaction is carried out, multiplied by the entropy change of a reaction, which we learned how to calculate in video number 1, from the enthalpy change of reaction. Therefore, the Gibbs free energy change of a reaction is calculated by subtracting the multiplication product of temperature multiplied by the entropy change of reaction and subtracting it from the enthalpy change of the reaction, all of which are measured under standard conditions. As stated here, I just stated that the units for the enthalpy change of a reaction are in kilojoules per mole. But we learned in video number 1 that the entropy change of reactions, the unit of which is in joules per mole Kelvin. And this is the only trick in this equation. Normally, the equation would be listed in the data booklet without dividing the entropy change of the reaction by 1000. But I prefer my student learn it with the division over 1000 to convert the units of joules here to kilojoules per mole, so that it is aligned with the units of the enthalpy change of a reaction, and to produce the units of the Gibbs free energy change of a reaction in kilojoules per mole. Therefore, once you calculate the entropy change of a reaction, it should always be divided by 1000 when substituted into this Gibbs free energy change mathematical equation to correct the units of the entropy change of a reaction. The unit of temperature is always in Kelvin, and both these units of Kelvin would cancel each other out, and thus the overall unit of the Gibbs free energy change of reaction would be in kilojoules per mole. Thus, using this simple equation, once you calculate the enthalpy change of a reaction and the entropy change of a reaction and include the temperature at which the reaction is carried out, one can determine if a reaction is spontaneous at that particular temperature or not using this equation. If once calculated, the entropy change, the Gibbs free energy change of a reaction produced is a negative value, this means that the reaction is a spontaneous reaction at that given temperature. Thus, if delta G of a reaction is negative, as displayed here, the reaction would be a spontaneous reaction at that given temperature. While if the calculated Gibbs free energy change of a reaction is a positive value, that means the reaction is not non-spontaneous at that particular temperature. I will cover an example as to how to calculate the Gibbs free energy change of a reaction at the end of this video. I would like to discuss this equation more in depth regarding the signs of both the enthalpy change of a reaction and the entropy change of a reaction and their effect on the overall sign of the Gibbs free energy change of a reaction. I've listed different combinations for the signs of the enthalpy change of a reaction as well as the entropy change. The enthalpy change here is listed as positive, while the entropy change is listed as positive on this side. On other instances, the enthalpy change could be negative, while the entropy change is negative. Another example would be the enthalpy change being positive, while the entropy change being negative, and the last but not least example in which the enthalpy change could be a negative value and the entropy change could be a positive value. One thing I like to point out to my students is that when the signs of the enthalpy change and the entropy change are both the same as in the first two lines here, in which it's positive and positive and negative in the second line, the spontaneity of a chemical reaction is affected by the temperature. While when their signs are different, temperature has no effect on the spontaneity of the reaction, and this is a much easier way to remember these signs. Let's consider the first example in which the enthalpy change is positive, while the entropy change of the reaction is also positive. In this case, you should consider the sign of both the enthalpy change, the overall sign of the enthalpy change of the reaction, as well as the overall sign of this multiplication product of temperature multiplied by the entropy change, taking into account the negative sign over here. Thus, if in the first example, if the entropy change of the reaction is positive, and it's multiplied by the temperature in Kelvin, which is always a positive value, the product of the T delta S would be a positive value, but once it's multiplied by this negative sign, the overall sign of this equation would be a positive value, while a negative value, and when taking into account the enthalpy change, which is a positive value, thus the Gibbs free energy change of reaction would be negative, would be negative if the temperature is really high. Because if the temperature is really high, then this overall negative term would be larger than this positive term, producing a negative Gibbs free energy change of the reaction. And this is why it's stated here that in this case, when the enthalpy change of the reaction is positive and the entropy change is positive, the reaction would be spontaneous at high temperatures. Thus, the delta G would be negative at high temperatures, since this product over here, the multiplication product of T delta S, taking into account this negative sign, would be a large negative value, much larger than this positive value if the temperature is really high. On the other hand, in this second example, if the enthalpy change was negative and the entropy change was negative, thus the sign of the enthalpy change would be negative, and the sign of this term over here would produce a positive value, since the negative entropy multiplied by this negative sign over here would produce an overall positive sign for this negative T delta S term over here. And thus This reaction would be spontaneous when the enthalpy change is more negative than when the multiplication product of this term over here is more positive. This would occur at low temperatures. If the reaction was carried out at low temperatures, this value would be a low negative value, and the enthalpy change would be, sorry, this value would be a low positive value, since negative multiplied by negative would produce an overall positive value, and the enthalpy change of the reaction would be more negative than this term is positive, producing once again a negative Gibbs free energy change of reaction, and therefore the reaction would be spontaneous at low temperatures. Therefore, when a reaction involves an enthalpy change that is positive and an entropy change that is positive, this reaction would be spontaneous at high temperatures. But since the delta G would be negative only at high temperatures. On the other hand, if the value for the enthalpy change was negative, and the value of the entropy change was negative as well, the delta G would produce a negative value at low temperatures. And as I stated previously, when both signs of the enthalpy change and the entropy change are the same, such as in this case positive, positive, negative, and negative, the spontaneity of the reaction is affected by temperature, such as here spontaneous at high temperatures, spontaneous at low temperatures. But when they differ, when the signs are opposites and they're not the same sign, the temperature has no effect on the spontaneity of the reaction. Let's explore these last two examples. In this example, we will consider a positive value for the enthalpy change of the reaction and a negative value for the entropy change of the reaction. A negative sign for delta S multiplied by negative would produce a positive value, and since the enthalpy change is also a positive value, thus the sign of delta G produced would always be a positive value and independent from the temperature, as I stated previously. And therefore, these types of reactions in which the enthalpy change is positive while the entropy change is negative would never be spontaneous at any temperature. Never spontaneous, because the value for the delta G produced would always be a positive value. On the other hand, in the last but not least example over here, when the enthalpy change of reaction is negative and the entropy change of the reaction is positive, the value for the delta G produced would always be negative, and therefore this reaction would always be a spontaneous reaction regardless of the temperature at which it's carried out, since a positive value for the entropy change of reaction multiplied by a negative value would produce a negative sign for this term, and since the enthalpy change is also negative, then the Gibbs free energy change of reaction produced would always be a negative value, and thus this reaction would be rendered always spontaneous at any temperature. You can memorize these or understand them, but you will be asked to predict if a reaction is spontaneous at high or low temperatures, or whether it's never spontaneous or always spontaneous, and be able to explain it in terms of the sign of the overall term of negative T delta S when compared to the sign of the enthalpy change of the reaction. This mostly covers the spontaneity of several different examples of reactions in which the signs of the enthalpy change and entropy change has been explored. I have stated here once again, if we were to consider the first two examples in which the signs of the enthalpy change and the entropy change of reactions are the same, whether they're positives or negatives, as I stated, that the spontaneity of the reaction is affected by the temperature. For example, if we were to take the first example, which is spontaneous at high temperatures, thus the delta G value would be negative at high temperatures. Therefore, if the temperature is decreased gradually, eventually the sign of delta G would flip to being a positive side, and the reaction at a certain temperature would be rendered non-spontaneous at low temperatures. That temperature at which there is a transition from spontaneity, from being a spontaneous reaction to non-spontaneous, or the other way around in the second example, a transition from being non-spontaneous, for example, to spontaneous. Basically, the temperature at which a transition in spontaneity of a chemical reaction takes place is called the transition temperature, and you will be asked to calculate this temperature for chemical reactions in which their spontaneity is affected by temperature. I've stated this here. For reaction in which their spontaneity is affected by temperature, there will always be a temperature below which or above which the reaction shifts from being spontaneous to non-spontaneous. This temperature is called the transition temperature, at which the Gibbs free energy change of the reaction equals to 0. Therefore, to calculate the transition temperature, one should equate delta G as 0 in the reaction in this chemical equation. This I've stated here. One can thus calculate the transition temperature of a reaction by equating the Gibbs free energy change as 0 as displayed in the equation below. Delta G equals delta H minus T delta S divided by 1000. At the transition temperature, delta G equals to 0, as you can see here. I've equated delta G as 0, and this and if the values of both the delta H and the entropy change of reaction are known, one can calculate the temperature at which the reaction transitions from being spontaneous to non-spontaneous or vice versa. A more general equation, instead of equating 0 in the equation, to calculate the transition temperature of any chemical reaction in which its spontaneity is affected by temperature, one should divide the enthalpy change of the reaction divided by the entropy change of reaction divided by 1000 once again, since the delta H units over here is kilojoules per mole, while the unit of delta S, the entropy change, delta S over here, is joules per mole Kelvin, and therefore it should be divided by 1000. The resulting units of temperature of the transition temperature would be in Kelvin, and thus if you are asked for this temperature in degrees Celsius, you should convert the temperature units to degrees Celsius. I will solve an example from your book, which is a worked example in the book. I've placed this over here. In this example, we are given a chemical equation with the state symbols as well as its stoichiometric ratios. 2 moles of magnesium nitrate solid decompose into 2 moles of magnesium oxide solid plus 4 moles of nitrogen dioxide gas as well as 1 mole of oxygen gas. And we are asked to, using the following data given over here, to work out the Gibbs free energy change and hence decide whether or not the reaction will be spontaneous at 25 degrees Celsius. As you can see in this equation, the reactants are made up of solids, while gases are produced in the products, and therefore the entropy change of this chemical reaction is the entropy during the process of this chemical reaction increases, and thus the sign of the entropy change for this reaction, once calculated, should be a positive sign, since there is an increase in entropy in this chemical reaction because it produces gaseous moles when compared to only solid reactants in the reactant side. We are given the enthalpy change of formation values for both reactants and products, and this is, since this is already in its pure elemental form, the enthalpy change of formation from its elements is 0, as we covered in previous videos, and therefore to calculate the enthalpy change of this reaction, we will be using enthalpy change of formation values, and thus we should form an enthalpy change of formation cycle, or using the general equation listed over here to calculate the enthalpy change of reaction using enthalpy change of formation values, which is the sum of the enthalpy change of formation of products subtracted from the sum of the enthalpy change of formation of reactants values given over here, and these values are per mole, so they should be multiplied by the correct stoichiometric ratios listed in the equation. I have 2 moles, I have 2 moles of magnesium nitrate, I have 2 moles of magnesium oxide, 4 moles of nitrogen dioxide, and 1 mole of oxygen gas. We are also given the absolute entropy values in joules per mole Kelvin of all reactants and products, which are all positive values, as we discussed in video number 1. And once we calculate the entropy change using the general equation listed over here for calculating the entropy change of reaction, which is the sum of the absolute entropy of the product subtracted from the sum of the absolute entropy of the reactants. One can calculate the Gibbs free energy change of the reaction. Therefore, to calculate the Gibbs free energy change of the reaction, we would need to use this equation over here, which is delta G equals delta H minus T delta S divided by 1000. In order to calculate delta G, we need to initially calculate the enthalpy change of the reaction as well as the entropy change of the reaction using the values given, and we are given the temperature in degrees Celsius over here at which the reaction is carried out. Therefore, the first thing I did over here using the values above was to calculate the enthalpy change of the reaction using enthalpy change of formation values by subtracting the sum of the enthalpy change of formation of reactants from the sum of the enthalpy change of formation of products. The products are MgO, NO2, and O2. O2 has no enthalpy change of formation, and thus I multiplied the enthalpy change of formation of magnesium oxide, which is negative 6O2 by 2 by the molar ratio, and I added to it the value for the enthalpy change of formation of 4 moles of NO2, which is 4 multiplied by 34. Then I subtracted the enthalpy change of formation of the reactants, which is magnesium nitrate, given as negative 790, multiplied by its molar ratio to produce a positive enthalpy change of reaction, the units of which are in kilojoules per mole, as stated over here. The second step, using these values over here, I calculated the entropy change of the reaction, which making sure to multiply their values by their molar ratios, and thus I multiplied the values of the absolute entropy of the products, which is 27, 240, and 205, multiplied by their molar ratios, and I subtracted the absolute entropy of the reactants multiplied by their molar ratio over here, and it produced a positive entropy change of reaction, as I discussed earlier, since this reaction produces gaseous products, and thus there's an increase in entropy represented by a positive sign for the delta S of reaction, the units of which are in joules per mole Kelvin. Once these values are calculated, I can calculate the Gibbs free energy change of the reaction by substituting the values into this equation over here. I have the enthalpy change of the reaction that we calculated, which is positive 512 kilojoules per mole, and I subtract the multiplication product of the temperature in Kelvin. We are given the temperature as 25 degrees Celsius, which equals 298 Kelvin, as placed over here, and I multiplied it by the entropy change of the reaction, which was a positive 891, divided by 1000 to convert the units of the entropy change to kilojoules per mole, and it produced positive 246 kilojoules per mole. And thus, since the sign of delta G is positive, then this reaction is non-spontaneous at this given temperature, and non-spontaneous at this given temperature. As you can see, the signs of both the enthalpy change and the delta S is the same, positive and positive. Therefore, this reaction spontaneity is affected by temperature change, and in the next section we are required to calculate the transition temperature, or the temperature above which or below which the the reaction transitions from being non-spontaneous to spontaneous. As the temperature is increased from absolute 0, work out the temperature in degrees Celsius at which the reaction first becomes non-spontaneous. Since we already determined at 25 degrees Celsius, 298 Kelvin, this reaction is non-spontaneous because it produced a positive delta G value. But increasing temperature, since both, as stated previously, since the signs of both the enthalpy change and entropy change are positive, as stated here, then this reaction would become spontaneous at higher temperature, and we are asked to calculate the transition temperature, the temperature above which this reaction becomes spontaneous. To do so, we will use the equation I discussed previously. To calculate the transition temperature, we simply divide the enthalpy change of the reaction divided by the entropy change of the reaction divided by 1000 to correct the units of the entropy change of the reaction. The value for the enthalpy change calculated was positive 512, while the value for the entropy change of the reaction calculated was positive 891, which I divided over 1000 here. This produces a value of 574.6, and as I stated previously, the units of which are in Kelvin. We are asked to calculate the transition temperature in degrees Celsius, and thus to convert it to degrees Celsius, I subtracted negative 273 Kelvin from this reaction to produce a rounded figure of 302 degrees Celsius. These are the type of questions that you will be asked in exams. You will be asked to calculate to determine the spontaneity of a chemical reaction using the Gibbs free energy change equation, and thus you should be able to calculate the enthalpy change of the reaction as well as its entropy change and substitute them into this equation using the correct units as well as using the temperature stated in the question. And you will also be asked to determine the transition temperatures for reactions in which their spontaneity is affected by temperature, which is when the signs of both the enthalpy change and the entropy change are the same. Whether they are both positive or both negative, the next part of the question will involve to calculate the transition temperature. If the signs of both the enthalpy change and the entropy change are different, then as stated here, these two reactions in which the enthalpy change and the entropy change signs differ. These reactions' spontaneity are not are independent from the temperature at which the reaction is carried out, and thus you will never be asked to calculate the transition temperature. This covers the section of subunit of 5.5, entropy and spontaneity. Please, I have attached a worksheet regarding this subtopic. Please solve the worksheet and submit it by midnight tonight. Thank you for watching.